Measurements are never 100% accurate because of equipment error and because of human error. For example, 20 centimeters is measured to the nearest centimeter. We want to calculate the upper bound and the lower bound for the measurement. Let's consider 20 centimeters to the nearest centimeter. Basically, let's think about things that would round to 20 to the nearest centimeter. You could have, for example, 19.6. That would round up to the nearest centimeter to 20. If we had, let's say, 20.4, that would round down to 20. So there's a whole range of values that would round to 20 to the nearest centimeter. And if we think about 19.5, that would certainly round to 20 to the nearest centimeter. But if you had 19.49, to the nearest centimeter, this would round down to 19 because the 4 would tell the 9 to round down. So the smallest value we could have that would round to 20 would be 19.5, and we call that the lower bound. On the other hand, if we had, say, 20.4999, that would still round to 20 to the nearest centimeter, and we could add as many 9s as we wanted to, which means that we can get as close as we want to 20.5, and our value will still round down to 20. So because we can get as close as we want to 20.5, we actually say that the upper bound is 20.5. So if we notice, to get the lower bound, we've taken away 0.5, and to get the upper bound, we've added 0.5. And this is usually what we do, or this is actually always what we do, but it's that we don't always round to the nearest centimeter, depending on the question. So the upper bound here is 20.5, and the lower bound is 19.5. So we've basically done 20, add half a centimeter to get to 20.5 for the upper bound, and we've taken away half a centimeter to get 19.5 for the lower bound. Here's a harder example. 10 kilograms is measured to the nearest 5 kilograms. Calculate the upper bound and the lower bound for the measurement. We're going to do the same sort of thing, but this time, because we're measuring to the nearest 5 kilograms, we need to halve 5, because last time we halved 1 centimeter, so we halve 5 to get 2.5, and we take away 2.5. So to get the upper bound, we do 10 plus 2.5, which is 12.5 kilograms. And to get the lower bound, we subtract 2.5, which will give us 7.5 kilograms. So essentially, whatever we measure to the nearest, so this is the nearest 1 kilogram, this is the nearest 10 centimeters, whatever you are measuring to the nearest, you halve, and you need to take that away for the lower bound and add it on for the upper bound. Please have a go at these questions now, and when you're ready for the answers, press play. Here are the answers. Very often, we need to use our knowledge of bounds to solve problems. Here's an example. The curator of an art gallery is displaying pictures along a corridor. The pictures are to be in a single row with no gaps between them as shown. The pictures are all square with sides of length 20 centimeters correct to the nearest 0.5 centimeters. The length of the corridor wall is 3,000 centimeters, correct to the nearest 10 centimeters. We want to calculate the smallest number of pictures and the greatest number of pictures that can be fitted in the row. To work out the smallest number of pictures, we need to think about the worst case scenario. And this would be when the pictures are as wide as possible, so we're looking for the pictures to be as wide as possible, and for the corridor to actually be as narrow as possible, because in that case you'd only be able to fit the least or the fewest number of paintings. So let's work out what the widest possible width, which is the upper bound of the width of the paintings, would be. So the pictures are all square with sides of length 20. So the sides are length 20, but it's the nearest 0.5. So I'm going to work out the upper bound of the width of each painting, which would be 20 plus half of 0.5, which is 0.25. This gives me 20.25 centimeters. The lower bound for the width of the corridor is going to be 3,000, take away half of 10, which is 5, so we get 2,995 centimeters. To work out how many pictures would fit, we need to do 2,995 divided by 20.25, because we're trying to see how many of the pictures will fit into the 3,000 centimeter space, or in this case the 2,995 centimeter space. So we do 2,995 divided by 20.25. We need a calculator for this. And that gives you 147.90. But you can't fit 0.9 of a painting into the space. You couldn't have 0.9 of a painting. So we can only fit 147 paintings. So in fact, let's write that in full. So we have this equal to 147.90 and so on. So we would say 147 paintings is the smallest number of paintings that would possibly fit. On the other hand, to work out the greatest number of paintings, we would need to work out first what is the least possible width, or the lower bound of the width for the paintings, and the upper bound for the width of the corridor, the length of the corridor. Because then you've got the maximum amount of space in which to fit the paintings, and the paintings are as narrow as possible. So first of all, let's look at the upper bound for the paintings. Sorry, the lower bound for the paintings. Just done the upper bounds. So the paintings they have sides of length 20 centimeters. The lower bound is going to be 20 because it's the nearest 0.5. Take away 0.25, which is half of 0.5, which gives us 19.75 centimeters. The upper bound for the length of the corridor is 3,000 plus 5, because we have half of 10, which is 5, which is 3,005. So to work out how many paintings can fit under these conditions, we would do 3,005 divided by 19.75. This is 3,005 divided by 19.75, 152.15. And again, I would write this down, but remember, you can't have 0.15 for painting. So in this case, the maximum number of paintings would be 152. Here's a question for you to try. Please pause the video now and have a go at it, and when you're ready for the answers, press play. Okay, let's go through the answers. The smallest number of lockers that could fit should be 132, and the largest number of lockers that could fit is 134.